Okay, in our previous presentation, we talked a little bit about some basic chemistry. We're going to expand on that now and look at some organic chemistry. We do have to get some terminology here. First off, organic chemistry, or organic compounds, are compounds that contain carbon. Most are covalently bonded. They have carbon, hydrogen, and oxygen, typically. An example is C6H12O6, which is glucose. Now, you don't have to remember that formula, but one thing you should be aware of is that these are fairly complicated compounds, whereas inorganic compounds, inorganic substances, lack carbon. They tend to be simpler compounds. For example, H2O, which is water, only contains 3 atoms, whereas the glucose has 24 different atoms associated with it. Now, a little bit about some of the inorganic compounds first, and then we'll jump into the organics. One of the most important inorganic compounds is, in fact, water. It is the most abundant of the inorganic compounds. It makes up about 60 to 70% of our body weight. And it's critical, very important, because it has some unique qualities. It has a high heat capacity. That is, you can apply a lot of heat to water and it doesn't change temperature very quickly at all. You've heard of a wash pot never boils. Well, that's what we're talking about. As a result, our body temperature doesn't change very much when we move from one environment to another. It has polarity, and we talked a little bit about that in the previous chemistry discussion, and that polar bonded materials make great solvents. And in fact, this is an excellent solvent for ionically bonded things, electrolytes. It is chemically reactive. That is, it takes part in a lot of chemical reactions. The easiest thing that we can do when we want to break something apart is to add a bit of water to it. And if we want to stick two things together, we take a molecule of water out and take the exposed areas where the water was and stick them together. Because water has this polarity, it likes to stick together. And as a result, water has a surface tension, so it acts as an excellent cushion. And so we have some sort of viscous cushions in our joints as a result of that. Some other important inorganic compounds include the salts. Now, salts are ions. They're ionically bonded substances that easily dissociate the presence of water. So, a salt is an ionically bonded substance, also known as an electrolyte. And electrolytes are vital for many of our body functions. We have to have sodium and potassium, for instance, to make muscles and nerves work. We have to have calcium so that blood can clot and that nerve signals and muscle activity can occur. Now, the definition of an electrolyte, the reason it's called an electrolyte, is that if you were to take an electrical current, 2 wires, and you were to put it in distilled water, that current would not flow. But if you stir in an electrolyte, if you stir in a salt, then electricity can flow through water. Now, part of the reason for this is that we have these charged ions. We have sodium here and chloride here, and they are separated by the water, and we are able to get electrons to kind of jump between these ions when they are dissolved in a liquid medium. Other important ionic compounds, or important inorganic compounds, are acids and bases. Now, an acid is not the liquid itself, that's water. But when you mix an acid with water, what happens is that it binds to one part of that water. It binds to the OH portion, releasing an extra hydrogen ion. Hydrogen is highly reactive, wants to bind to other substances, and that's why we have an acid. Now, I don't care that you know that it's a proton donor or anything like that. Bases, these are substances that when mixed with water will bind to the hydrogen, releasing this hydroxyl ion. Now, acids and bases are equally reactive. Acids react a little faster because their molecules are smaller. There are reactions that can occur that you can neutralize acids and bases. Basically, you mix an acid and a base, and they will react together to form water, and usually a salt. So there are some salts, NaOH and HC. That's a base, and HCl, which is a acid, and you mix those together, and you get water and salt, table salt, basically. Now, we measure the relative concentration of the hydrogen in an acid or a base by pH. And this is a logarithmic scale that goes from 0 to 14, with middle pH of 7 being neutral. Any number that is less than 7 is an acid, which means that there is a higher concentration of hydrogen. Anything that has a pH higher, or a number higher than 7, is a base, which means that it has a higher concentration of the OH ion. Now, we do have in our bodies some substances called buffers that regulate pH changes. These are substances that, in the presence of an acid, will bind to the acid. In the presence of a base, they will actually release a hydrogen, which can bind to the base. And so we have a variety of these substances in our bloodstream to keep our pH within the appropriate range. Now, I mentioned earlier that this is a logarithmic scale. Now, what that means is that a pH of 4 is not twice as acidic as a pH of, 5. If we go from, say, 6 to 5, that's one step. The next step from 5 to 4 is not the same. Each step is 10 times the previous step. So if we started out with an acid with a pH of 6, then an acid with a pH of 5 is 10 times stronger than an acid with a pH of 6. Acid with a pH of 4 is 10 times stronger than an acid with a pH of 5, which means it's 100 times stronger than an acid with a pH of 6. And so we could say that from a pH of 7, we go 10 times more acidic to a pH of 6, 100 times more to a pH of 5, 1,000 times more to a pH of 4, 10,000 times more to a pH of 3, 100,000 times more with a pH of 2, 1,000,000 times more with a pH of 1, and 10 million times more with a pH of 0. So you can see that these steps are just big changes as opposed to little bitty ones. Our bodies have to stay within a very fine range, very narrow range of 7.35 to 7.45 on our pH scale. We are slightly basic. Now, I don't expect you to know all of these substances. I do expect you to know one, and that is distilled water. Distilled water is the substance that has a pH of 7, and it is neutral. Other substances are not going to have that neutral character to it. So pure water is neutral. So just to sum up acids and bases, we have a scale from 0 to 14. Any number that is 7 or less than 7 is an acid. Anything that is greater than 7 is a base. pH of 7 is pure distilled water, which has a neutral pH. When we say something is an acid, we are saying that there is more hydrogen ion in the liquid. If we say something is a base, you have a higher hydroxyl on them. That is an OH group. It is a logarithmic scale, and so you should know that each step is a step of 10. So if I were to ask you on a test, if I gave you an example that said, something with pH of 6 and another substance with a pH of 3, several questions that can come out of that. I could ask, which is more acidic, and that would be the one with a small number, the pH of 2. I could say, how much more acidic is the substance with pH of 3 as compared to a pH of 6? And to do that, just count. We've got 6, 5, 4, 3. So 3 there. You just add that many zeros. You take a 1, add 2 zeros. A pH of 3 is 1,000 times more acidic than a pH of 6. A pH of 2 will be 10,000 times more. Just count down and subtract one number from the other and add that number of zeros to the number 1, and you're going to get the difference in acidity or concentration. Now, when we talk about the inorganic compounds, we're going to start talking about the organic compounds, but I think that this is a good point to stop on this presentation. We'll pick up on the organic compounds in our next presentation. Thank you much.